Spanning tree protocol. What is it? What does it do? How does it work? These questions plus more we'll be going through in this video, and you will learn everything you need to know about this layer 2 protocol. Hey everybody, and welcome back. I'm David Townsend from the Net Academy, where we are learning networks together. And on this video, what I'm going to be going through is Spanning Tree Protocol, or STP. Now honestly, STP does have a bit of a bad reputation. You know, a lot of people like it, and that's because of what it does. What it does, one of the many things it does, is it blocks links. It blocks traffic going between two switches over a link for that VLAN. Why would you want to do that? We'll of course go through that in the video. There are advantages to STP, but there are also some disadvantages to it as well. That's why a lot of networks try to stay clear of STP and all of its variations as much as possible. So it does have a bit of a bad reputation, but it does bring benefits to the table at the same time. And in this video, what we're going to be going through is what really does STP do? What are the benefits it brings? What are those challenges it actually resolves initially? And we are going to build the foundations and build up. We're going to go through what is a routing bridge? What is a bridge identifier? How is a route bridge actually elected? What are all the different port states and port types you can get in the STP world? And then we're going to go through a bit more advanced stuff where we're going to go through what happens when there's a topology change. What are those timers and what are those frames that are going back and forth? So really, doesn't matter if you're going towards your JNCIA to your JNCIP, or from your CCNA in the Cisco world to your CCNP, or the new NCORE Enterprise Core exam, the information will be the same, because STP, or Spanning Tree Protocol, is part or from an open standard. It comes from IEEE 802.1d, and that means that all vendors, Juniper, Cisco, Arista, whoever, it doesn't matter, have to support that protocol to the letter. You can't do any deviations of it because it's an open and agreed standard. Yes, of course, the configuration on those vendors is going to be different, but the protocol itself remains the same, and thus the theory remains the same. So we're going to start off with the foundations and build up from there. But enough of me talking, let's actually just get straight, and I'm going to warn you here, straight into a few slides, but I'll make it as interactive and fun as possible, and of course informative, and let's build up from there. And here we go, straight into the theory as always, because you have to understand the theory, you have to know the theory before you could do any configuration, or at least that's the way I work. So what you could see here, of course, we've got 3 or 4 switches. Gosh, Striff, I need to go back to school and learn to count. But we've got 4 switches, SW1, SW2, SW3, and SW4. And what you can obviously see is that they've got a connection, a point-to-point connection to and from each one of these switches. And these connections would all be layer 2, or L2 for short. And when we're talking about layer 2, typically we're talking about Ethernet. We're talking about Ethernet frames. So forget IP, forget all those routing protocols. This is layer 2. The world of IP doesn't really exist when we're talking about layer 2, and especially about STP. And what I want to do is I first want to go through what are the challenges when it comes to a network that doesn't use STP or any of its variations. So let's just say, for example, that we've got a host here, David Townsend, and he has a wired connection into SW1. And maybe he's doing or utilizing some kind of application. You know, maybe David Townsend is doing a Microsoft Teams call or whatever it is. But when you talk about Microsoft Teams as an application, this is a form of bum traffic. Bum, yeah, I know, jokes aside, but broadcast, unknown unicast, and multicast traffic. For those of you who don't know what they are, broadcast is literally when you've got a frame and you're going to send it to everyone. It's literally a flood all. Broadcast just means get it out there. It's going to go to all recipients. It's going to go to all devices in that same VLAN, in that same network. Unknown unicast is when you don't know the destination's address. It's an unknown unicast, i.e. it's from one device to another device, from one single point to another single point in the network, but they don't know where that destination, what that destination MAC address is. And multicast, the M in BUM traffic, just basically means that it's going to a few or quite a few interested parties, devices, and destinations in that same VLAN. So broadcast, everyone, unknown unicast, to one device, but you don't know the destination address. And multicast is where it goes to a few or quite a few interested devices in that same VLAN, and of course the address is known. But when we talk about Microsoft Teams, this is a form of BUM traffic. Honestly, I don't know if it's broadcast or multicast. It really doesn't matter. But if we follow this approach where David Townsend's Microsoft Teams with the video and the typing and screen sharing, etc., it comes into SW1 and it sees a BUM traffic, whatever that is, broadcast or unknown unicast or multicast. And what does it do? And let's say the destination is down here. So maybe this is the port to the internet facing router, whatever it is. This is just a high level example. What SW1 is going to do is it's going to say, you need to get to the destination, which is down here. And because this is a BUM traffic, I'm going to send it out of this port. And I'm also going to send it out of this port here. Now, at this point, SW2 and SW4, they will send it on to the switch W3, SW3. But because it's BUM traffic, what will happen next, and let me get a different color, is that the frames will continue to go around the network like this. And you can see what's happening here and in the opposite direction as well. What have we suddenly got going across our network? We've got a loop. So whether we're talking about layer 2 or layer 3 or any layer for any application, this is one thing you absolutely want to avoid in any network, is this layer 2 loop. So the challenges without STP is that you are going to get these multicast and broadcast storms. It's just inevitable. You're not going to be able to get around that. You're not going to be able to stop that without STP. But what is this MAC table instability? Well, again, let's just say I'm up here, David Townsend has a connection into SW1 and I want to get to a destination which is connected to SW3. Doesn't matter what that destination is, let's just say it's a destination, whatever that is. So I want to send a frame. The MAC address is known, the switch W1 knows where to send it, and it will send it out of SW1 to SW2. SW2 then sends that frame down to SW3, where it then gets to the destination. Great. Well, what SW3 learns in its MAC address table is that to get to David Townsend, and I'm just going to put DT as short, I need to go out of, and let's just call it Gigi 00, I need to go out of my Gigi 00 port. But what happens when I send the next frame for a different application? SW1 at that point might then send it down to SW4, who sends it on to SW3. But then suddenly SW3 is saying, hang on, I'm now seeing you on this interface here. And let's call that gig 01 just for example. So at this point it's going to say, hang on, I need to update my MAC address table, and David Townsend, I could get to him via Gigi 01, whatever the interface. But then another frame comes in and SW2 sends it down. And now he can see, he's now back on Gigi 000. So let me put that back, and he's now connected to Gigi 00. And then another frame goes. You can see where I'm going. It goes back and forth, and it has to keep updating its MAC address table. And that's where you get this instability. You obviously don't want that in any network. You don't want any loop in any network, and you don't want any instability. In networks, generally, we like things to be as stable as possible. So how does STP get around these challenges? Well, what it will do, essentially, at the end of the day, without all the theory aside, is it will block one of these links. Whatever the link is, it will put it into a particular type of state where it's just going to say, for this VLAN, any traffic that's coming from SW1 over to SW2, I am going to block that interface on SW2. And so therefore, we're not going to have bump traffic going around the network, and we're not going to have MAC table instability where SW3 was constantly having to update its MAC address table. That's what Spanning Tree Protocol, or RSTP, MSTP, and all the variations, regardless of vendor, does at the end of the day, is it blocks ports, it blocks interfaces. That is not a good thing. That's why a lot of people are moving away and try to stay away from STP as much as possible. And that's why I said it's got a bad reputation because of this. But it does what it does, and it does so very, very well. So even though it's got a bad reputation, it is a bad reputation that has been well earned because it does its job very, very well. But here's the question. How does it know what port to block? In such a simple topology as this, yeah, it's okay. It's easy to figure out once we know the theory. But what if it's a larger network, or even this type of network? There needs to be a device that all devices agree on and that this tree branches out from. And that's really the concept of this spanning tree, is that there's going to be one path from this particular device to all leaf devices, and that is going to span across all devices. So you've got the root and you've got the leaves, and we're going to have one path, one direction as such. I can't believe I just said one direction. I really don't like that band, not that they're around anymore, but we're going to have one path to get from that root to that leaf, or those leaf devices, and all redundant links will be blocked, preventing those challenges. And I just said a key word there, root. In Spanning Tree Protocol, there's a concept of a root bridge. And as I just said, there's this concept of a root bridge, and that is to ensure there's only one available path from that root to the leaf. That is the concept. That's really where the term tree came from. We're going to have one direction, one path from root of the tree to all those leaf devices. And let's just say, for example, we've got root bridge SW1 here. All the other switches will be designated switches. So they will be a designated switch for that particular segment of the network. But really what people refer these switches as is the non-root bridge. So whether you call them designated switches or non-root bridges, to me it's really the same thing. A non-root bridge for SW4, for SW3, and of course SW2 as well. So the root bridge is really, I wouldn't say it's the master, but all of the non-root bridges, they're waiting to hear from the root bridge, from SW1, what is the configuration, what is the architecture, what's the topology like of this network. And once they start hearing these frames from SW1 across the interfaces, they will learn, what am I going to do with my interfaces? Am I going to forward traffic, or am I going to block traffic? There's obviously a few decisions in there, and just know that these frames that are going from the root bridge down to all these switches, they're what's called BPDUs, or Bridge Protocol Data Units. Now, specifically, this should be called STP BPDU, because Bridge Protocol Data Units you do get in other protocols as well. It's just the contents of that frame that really change depending on that protocol. So don't think BPDUs are just for STP. You do get BPDUs in other protocols as well. So as I said, it should be called STP BPDU, but really that's just a side point. But just know that these frames, which is controlling the architecture of the network, the topology really, and notifying of any topology changes, we'll go on to that, they're called BPDUs, and we'll go on to those contents in a bit. But for now, what is a root bridge? The root bridge basically ensures that there's only one available path from the root, from the base of that tree, to all other leaves by blocking an interface and getting around these challenges here. But here's a question. how is a root bridge actually elected? You can't just say, oh, I want SW1 to be the root bridge, and suddenly that works for obvious reasons. Any of these switches here, SW1, SW2, SW3, and SW4, could be a root bridge. Maybe you're okay with them deciding amongst themselves what is going to be the root bridge, or maybe you want to configure your network to determine that maybe we're going to have SW4 as the root bridge for that particular VLAN. So how is a root bridge actually elected? Well, there's something called a bridge identifier. And basically what this does is it gives a priority or a bridge priority, and also it identifies the MAC address of that switch, of that system. Note there, I did not say the MAC address of the interface. The bridge identifier, and this is abbreviated to BID, just so you know, it consists of that priority value and it consists of the MAC address. But that MAC address is not of the interface. It's not of this interface here, and it's not of this interface down here, and it's not of that interface. Nope, it's none of those. It's for that device itself. So not of the interface, but it is for that chassis. And as such, every bridge identifier should be unique because we're going to have different MAC addresses, of course. And what's this priority value here? The priority value really determines, well, what bridge has higher, or better, I should say, has better priority to be that root bridge. And typically, definitely, regardless of vendor, in the spanning tree protocol world, lower the value is more preferred. So if you've got a value of 0, just for example, this means that whatever that switch is, so say it's switch W4, that means SW4 will be the root bridge. If it's a value of 4096, means it might be. It's going to be very close to it. But if SW3 has a value of 4096 and SW4 has that priority of 0, guess what? SW4 is still going to be our root bridge, because lower the value, more preferred that switch will be to be that root bridge. But the interesting thing with spanning tree protocols, when you first initialize the system, when you first boot up this network, SW1 is going to send out of its ports, guess what? Those BPDUs, those bridge protocol data units, to say, hey, I'm the root bridge. And at the same time, SW2 is going to send out its BPDUs to the adjacent switches to say, hey, I'm the root bridge. And you can see where I'm going here. At the same time, SW3 will send out of its interfaces, its BPDUs, to say, hey, I'm actually the root bridge to begin with. And guess what? With SW4, it will send out its bridge protocol data units to the adjacent switches to say, hey, I'm the root bridge. So when you first boot up this network, when you first start up your spanning tree protocol configuration, every switch will assume that its root bridge will be the same as its own bridge identifier. What do I mean by that in English? Well, in the initial BPDUs which get sent out, so this is again in initial configuration, say SW4 is sending out those BPDUs, it's going to say the root bridge is SW4 and I am SW4, and therefore I am the root bridge for this network, for this layer 2 domain. But again, remember, how is a root bridge actually elected? It comes down to the priority first, and then who has the lower MAC address. So in both cases, lower priority wins, and if there is a tie, lower the MAC address wins as well. So first it will look at the priority, and if the priorities tie, it will then look at 2, what is the lowest MAC address. And so let's say that SW4 is going to be the root bridge, and it's received the BPDUs from SW3, and SW3 has also received SW4's BPDUs. Now at this point, the SW3's frames, those BPDUs, they're going to be what's called inferior. They're inferior because SW4 has a better priority. It has a lower priority value. Or maybe the MAC address is just lower if there is a tie. And as such, the BPDUs that have come in from SW4 will be superior to SW3s. So what happens at this point is that SW3 is going to send out of its interface updated bridge protocol data units to say the root bridge is SW4 and my bridge identifier is SW3. And all the switches do this. They do this back and forth and etc. until they all agree on what is that common root bridge. And at that point, I wouldn't say they're converged, but they're getting closer to converging. This is the first step in the spanning tree process, is selecting that root bridge. And here's a question for yourselves. I've just put in a little bit of information here. So we've got our bridge identifier here, and I've done three things. So you can see I've put in the bridge identifier, which consists of the priority value and also of the system's MAC address. So you've got priority here for switch W1 of 4096. You've got priority of SW2 as 8192. The priority of SW3 is 4000. I'm just going to say 4000. And the priority of SW4 is 0. Question for yourselves, which one will be the root bridge? Well, hopefully you all answered SW4 because that priority is 0. It is the lowest priority and thus it is definitely the most preferred priority. What would happen if, just for example, the priority of SW3 was also 0? Question for yourselves, what would happen? Well, don't forget, in the bridge identifier, there is the priority value, which is looked at first, and then it will look at, secondly, the MAC address. Again, the lower MAC address, that is what's preferred. And all of this is the bridge identifier. So what you've got to then look at is what is the lowest MAC address. So we've got AA, BB, CC 10, 11, 12 for SW4. And then we've got AA, BB, CC 778899 for SW3. Which one would, if there was a tie in priority, would be the root bridge? Would it be SW4 or would it be SW3? The answer is it would be SW3 because it has a lower MAC address, of course. And that is how a root bridge is actually elected. And again, to summarize, first it looks at a priority value. If there's a tie, it then looks at, secondly, the lower MAC address. And for me, I always asked a question, when we look at the priority value for that particular bridge identifier, I said it always increases in 4096 steps. You can't go 0, 1, 2, 3, 4. No, it's always going to increase in steps of 4096. Why is that? Well, when you look at actually that priority header, and all of this here is that priority header, we've got 4 bits, as you can see here, that actually do get assigned, that are used as identifying the priority of that bridge. And what you can see is that the first initial bit for these uppermost bits for the bridge priority is 4096. So if this was a 1, this would then be 4096. To get to here, so this would be enabled, we need another 4096. And if you add 4096 on top of 8192, you get to 12,000 and whatever that is. If you're wondering where you're getting 4096 and these numbers from, well, just remember right here, these are the not the number of bits, but they're what a bit would actually indicate. So the first bit, if it was a 1, would be 1. A second bit would be a 2, then a 4. And it's just multiplying by 2 every single time because a bit has 2 options, a 0 or a 1, as you can see, and thus it's always a power of 2. So then 16, 32, 64, and all the way up till you get to the priority field. So if you're wondering why you're always increasing the values of 4096, it's because of those 4 bits really when it comes to the bridge priority. And if you're wondering what the system ID is, and this is called different things in different vendors, so in Juniper world, it's called the Extended System Identifier. Don't ask me why. I don't know what it is called, honestly, in the Cisco world and other vendors. But what this is basically doing is it's identifying for a particular VLAN what is that priority for that particular VLAN. And this is pretty fascinating for me, because if you look at a VLAN with the identifier, a VLAN ID can support up to 4096 different values. Really, when we're talking about it, it's 0 to 4095 in terms of numbers, because 0 is a number. And if you add all of these options here up, all these numbers I should say, what do you think you come to? You actually do get 4095, and thus there's 4096 different options, again taking 0 into account. So that is why when you're defining the bridge priority, it will always increase by 4000 or 4096 to be precise, because of those bits that you have in that bridge priority. So yeah, how is a root bridge elected? Again, just to cement in, lowest bridge identifier wins. First, it will look at the bridge priority, and then it will look at the MAC address. Again, lowest always wins. So yeah, we now have got our root bridge. First step in the spanning tree process is discovering from all those BPDUs going back and forth who has the best priority, or the lowest priority, and agreeing on that bridge, that root bridge. And in this case, it is SW4. What is the second step in the STP process in terms of converging? The second step is really defining the port row and the port states. So under port rows, I'm not wasting any time here, you could see the 3 different type of port rows and the X amount, the 5 different type of port states. And obviously I will go through these one at a time. So we've got our root bridge here, and obviously SW1, SW2, SW3, they're going to be non-root bridges. They're going to be designated switches, however you want to think of them. What is a root port? Basically, the root port is the lowest or the best cost to get to that root bridge. So if you look at it from SW1's perspective, what is the lowest cost to get to the root bridge? If this has a cost of 4 and this has a cost of 16 to get to the root bridge, what is it going to prefer? It's obviously going to prefer this port here, and thus it will determine that this interface, whatever that interface is going to be a root port. If we look at it from SW2's perspective, again, it's got 2 different ways to get to the root bridge. And let's just say this route down here, we've got a cost of 4 on this interface here, and we've got a cost of 4 on this interface here, which of course makes 8. And let's say we've got a cost of 4 here and a cost of 8 here, which has a total, of course, of 12. Which way is it going to prefer? It's going to prefer this way, because this has the lowest cost. What does it do from SW2's perspective when this cost here is 8 and this cost here is 8? Well, what it then does, it's a process of determining which route am I going to prefer. So this is 8 in this direction, this is 8 in this direction, and then it's going to look at the next step in breaking that tie is actually looking at, guess what? The adjacent system priority. So SW2 can then see, SW1, you've got a value of 4096, and SW3, you've also got a value of 4096. So it then moves on to the next step, which would be actually looking at, guess what? The MAC address. Lower the MAC address, that's going to be preferred. But if the bridge ID of SW3 was, for example, 0, it will then forward those frames via this direction, because 0 is more preferred over this value here. In the STP world, lower is always better. And just a point on that cost, and it's really the next point coming up in this tutorial, but the cost is cumulative. It's not just total, it's something that builds up. So if this was a cost of 4, and we're again looking at it from SW2's perspective, SW1 can see, to get to that root bridge is going to cost me 4. But if this here was also a cost of 4, it's going to cost SW2, guess what? 4 plus 4, you get 8. So it's a cumulative effect. Lower the cost, that's always going to be preferred. But coming back to the root port is basically the lowest cost to get to that root bridge. So again, if this was a cost of 4, and this was from SW1's perspective to get around this way, a cost of 16, it's going to have this as a root port, and then it's going to put that interface in one of these 2 rows and one of these states actually here. What is a designated port? A designated port is a port that is not facing the root bridge. So we've got our, let's look at it from SW1, we've got our root port here, and let's say this interface here is going to be root port as well from SW2's perspective, and SW3 is going to have this interface here as a root port. The designated port is the interface that is not facing the root bridge, and I'll do this in a different color. So from SW1's perspective, on this interface here, it would assign this as a designated port. On SW4, it would actually have both of its own interfaces as designated port, because it can't have a root port because it is the root bridge. And between SW2 and SW3, one of these will be designated port and one of these will be an alternate port, i.e. a backup port. And that really then does depend on these states here. Now note, for these particular states, blocking here, as I've already said, that interface is being blocked. So that switch can actually receive BPDUs, and it wants to receive them to know that the adjacent switch on the other end of the link is still there and still active and alive, but it's not going to process them. It's not really going to do any learning. It really, in terms of operational states, it's between blocking and forwarding. These 2 steps here, these 2 states, are really transitional. So if a port is transitioning from blocking to forwarding, or from disabled to forwarding, it's got to go through the listening process and it's got to go through the learning process. I'll come on to those in just a second. And actually, no, let's do it now. So in the blocking state, we cannot send or receive frames. We cannot forward those BPDUs, but we can receive those BPDUs, as I was saying, but we are not doing any learning. But that listening and learning state, they're transitional, because when we go from a blocking to forwarding state, we've got to go via the listening state, and then we've got to go via the learning state, and then we eventually get to the forwarding state. Now in the listening state, we do not receive any frames. We do forward, if it is a designated port, BPDUs. So we are receiving BPDUs, but we are not learning the BPDUs. So if SW3 is sending over to SW2, let's say this port here was blocked, BLK for short, then it's not going to really receive and process those frames, but it's still going to listen in on those BPDUs to know that SW3 is there alive and active. And then it will transition to the learning state, where it's not sending or receiving frames out of that interface. It's can forward, it can be the word, it can forward BPDUs. We're receiving BPDUs, but now we are learning the MAC addresses that's contained in those frames. But again, we can spend a certain amount of time here, and then we're going to transition into the forwarding state, where we can send and receive frames, we can forward BPDUs, we can receive BPDUs, and we can really learn the MAC addresses therein. So both the blocking and the forwarding, these are what's known as stable states. That's where you just want them to ideally remain. And the transitional states for listening and learning are transitive. They're not going to be in that state, hopefully, for a very long time. And if you're wondering what disabled is just that interface is disabled on STP. It's not configured to be part of the STP process, and thus it is disabled. But here's the next 3 questions. How is a root port elected? I've already gone through this, but how is a blocking port elected, and what happens if you have 2 ports available to an upstream switch? Let's go through these one at a time. Well, I've already covered this first part here. How is a root port elected? This again comes back to cost. So if we know that SW4 is the root bridge, And if you look at it from SW2's perspective, it's got two paths, hasn't it? It's got one path here and it's got another path here. And it just knows that from those BPDUs, and it just can see that that cumulative cost in this direction is 8. Maybe this is 12. What's it going to prefer? Lower the cost. It's going to prefer this. And thus it just knows that actually this interface here is going to be the root port. And this interface here is not going to be a root port. What port is it going to be? It will be a designated port. That's the port row here. And if you're wondering what those link costs are, I've just actually taken this from good old Google. But here's the STP cost for a 4 gig link, for 10 meg links, 16 meg, 100 meg, and the list goes on. And you can generally see, note that the two here are really not entered, because I'll be surprised if you're getting 100 gigabits per second at the access layer in any network. That would be incredibly fast. Maybe in data centers, but you're not going to have STP in a data center, God forbid. But you can really see the faster the interface, the faster the speed, the lower the cost. So if this was 1 gig here, this would be a cost of 4. That would be a cost of 4. If this was 10 gig here, that would be a cost of 2. And maybe this was 1 gig with a cost of 4. And again, from SW2's perspective, what's it going to prefer? Well, it's obviously going to prefer this route because it is a lower cost of 6. And what you can see now is what I've done, because we know that SW4 is the root bridge. I've put all of those port rows, so you can see designated port here, and you can see root port here and here. And note all the root ports are in the forwarding state. They're sending, receiving, forwarding, BPDUs, receiving and sending frames. So that is a stable state. But note here, oh, and also note I've put in the link cost. Now note here for SW2, for this link right here, I've left this blank. Because the next question is, how is a blocking port actually elected? And what it really comes down to at the end of the day in the STP world is lower the better. So the first process in determining what is going to be the blocking port, the lower the cost, the better. So from SW2's perspective, to get to that root bridge, to get across to SW1, that's going to cost me 4. But from SW1's perspective, to get to the root bridge, that's going to cost him 4. So therefore, I know that in this direction over here, it's going to cost me in total 8. But what SW2 can also see, to get to SW3, that's going to cost 4. And from SW3's perspective, to get to the root bridge, it has reported to me a cost of 4. So that is also a cost of 8. So what then becomes the blocking port? Well, you can already see that this port here is blocking and in the alternate state, the alternate row, because it's a backup. But if there is a tie in the lowest path cost, it then looks at lower system priority. So let's look at it between SW2 and SW3. So we look at first first we look at the path cost, but then system priority. So this has a priority of 8192. This has a priority of 4096. Well, that's that at the end of the day. Because these two switches have exchanged those BPDUs and learned the priority and the MAC address, of course, they just know that SW2, you're least preferred because your priority is higher and thus not preferred. And so this interface here is going to go into blocking, but this interface here is going to go into, it's going to be a designated port, but I am going to be forwarding traffic and BPDUs. What if this was also 4K? So no longer 8192, it was 4096. Well, again, next part, lower MAC address wins. So if you look at the MAC address, SW3 ends in 778899, SW2 ends in 445566. What would be the blocking port? It would be down here. So we'd now be blocking on SW3's interface right here, and this would go into a forwarding state. So you can really see there just how changing the priority value, and having a lower MAC address can really then influence what ports are actually in that forwarding state and what ports are in that blocking state. But just remember, how is a root port elected and selected? It's the lowest cost to get back to that root bridge. How is a blocking port actually elected? First, it's done on the lowest path cost. If there is a tie, it will then look at, between those adjacent switches, who has that lowest or lowest priority. And if there's a tie in that priority, it will then see who has that lower MAC address. But what if there is two interfaces between SW2 and SW3? Well, that obviously changes things, because now we've got two links between the two same switches. So how are you going to know what to block? What's going to be a root port between two switches which has two links, two ports available between themselves? So when you look at the interfaces, i.e. we've got two links here between SW2 and SW3, the first thing it's going to look at is lowest priority. So first it will look at SW2's priority is 8,000 and SW3's priority is 4,096. So therefore SW3 is more preferred. But which port then becomes blocking? So let's just say this interface here is GIGI00 and this interface here is GIGI01. And every interface in the STP world will have a priority to it. The default, I believe, is 1 to 828. But you can configure these. So this interface here might have a priority of 0, and this interface here might have the default of 128. What is preferred? Well, in the STP world, lower is always better. So because this has a this GIGI00 port has a priority of 0 and this has a priority of 128, that means that this interface here is going to remain in the blocking mode, and both of these interfaces down here will be forwarding traffic and being a designated port. But what if this interface here had the priority of 0? Well, obviously there's a tie between GIGI00 and GIGI01. So what happens then if there is a tie? Lower the port ID, the more preferred it is. So in this case, the GIGI00 interface will win over the GIGI01 interface. So there we go. Quite a bit of information, I know. But just know from this one slide that STP is breaking the loops. And it's breaking the loops by assigning a port as blocking. Just not forwarding any traffic out of that, but still receiving BPDU, still wanting to receive BPDUs to learn the switch on the other end of that link is still there and still able to forward BPDUs to it. Come on to that in a few minutes. But to learn what links to actually block, we need to first elect, guess what, a root bridge. The root bridge is determined by first lower the priority, or it's more preferred, and if there's a tie, who has the lower MAC address. Once you've learned who's the root bridge, you can then start calculating, well, what's going to be my root port being the lowest cost from that switch back to the root bridge. And all the designated ports are basically the ports that don't face the root bridge, and the alternate port being, well, it's a backup in case the blocking port goes down or needs to transition to a forwarding state. And then you've got your states here. Ideally, you're either in the forwarding or the blocking state. I say ideally for blocking, because you need blocking, otherwise you're going to get these challenges here. But just always remember, in the STP world, lower is better. And here we go. Here is that glorious BPDU, or Bridge Protocol Data Unit. And this is really important to know, and with any frame, with any protocol, it's always important to know what's inside all of those headers. But if we bring it back, what is the function of a BPDU? Well, there's quite a few functions, as you can see. But as I initially described, if we look at it from SW4's perspective, it initially, when we started the STP process, it communicated over to SW3 its BPDUs saying, I am the root bridge. But at the same time, SW3 sent over to SW4 its own PBDUs, and then they started to agree on who was that root bridge, and this was happening between SW4 to SW1 and SW1 over to SW2 and SW2 over to SW3, etc, etc. And really the contents of these BPDUs is everything you see here. And recall, as I just said, when it comes to deciding and agreeing on who is that root bridge, there is header information inside of the BPDU, such as here, to describe who is that root bridge. But at the same time, you've also then got these other headers like bridge ID, which describes, hey, this is my own root bridge, or RB for short. And this is important because once all of these switches have decided on who is the root bridge, SW1, for example, if we look at SW1's BPDU, in its header information, it's going to say the root bridge is the MAC address of SW4, but my bridge ID is the MAC address of SW1, I think I said. So all of these headers serve a purpose, especially these timers here, and I will go on to those in just a few minutes. They're very important. And what I've done is I've just entered for you all of the more techie details, but keeping it high level as much as possible on what these individual headers for this BPDU actually mean. So let's start off at the beginning, the protocol ID. There's not really much you need to know about this other than it's basically identifying that this BPDU is for STP. It is for 802.1d. Remember I said you can get different BPDUs, different bridge protocol data units for different protocols. And really this protocol ID here is just identifying what is the identification of that protocol and the BPDU therein. The version, what this does is it actually identifies, are we using STP? If it's STP, it's using this hexadecimal value there. Or is it RSTP, or is it MSTP, or in the Cisco world, is it PVST, PVST plus, which are very resource intensive, I know, but regardless, the version is just identifying what is this version of spanning tree. Is it Common Spanning Tree Protocol, or STP, or is it RSTP, Rapid Spanning Tree Protocol? Is it Multiple Spanning Tree Protocol, tongue twister, etc, etc. You get the idea. And then we've got this BPDU type, this header here. Now there is only two options for this bridge protocol data unit type header. It's either a configuration or it's a topology change notification. Now this is important because we've gone through that SW4 was that root bridge. But what happens if, just for example, the interface here goes down? Well, SW1 is going to see that, isn't it? And what's going to happen, even though it's not the root bridge, it's going to communicate over to the root bridge, to SW4, that there has been a topology change notification, i.e. it's going to set the bits within this BPDU type to indicate that, hey, Mr. Root Bridge, there has been a topology change and I am notifying you of this. The other part of configuration is when, just very quickly, we're going to go into more detail and some examples of this in a few minutes, but when the root bridge has received this TCM, it's then going to send out its own BPDUs to all the switches connected within this layer 2 domain, a BPDU type, but it is going to be a configuration message. It's going to say, hey, there's a configuration change and you need to look at the contents of this BPDU. And building on top of that, so when you've got a configuration message, a BPDU type which is a configuration message, so we've said SW4, which is that root, has sent out of its ports a configuration BPDU, but what it's going to say in the flags field is that there is a topology change. So in that first case, and let's actually make this into an example. So this interface here has gone down. So SW1 will send up to the the root bridge to SW4, first it's BPDU with a topology change notification. So I'm just going to enter in 1 here to indicate it's a topology change notification. Now, what happens second to this is the root bridge will then send out of all of its ports, as I just said, its own BPDU. And this will be the second part, but this is going to be a configuration BPDU. So we're going to have configuration here, but we are going to have our flags set to include that it has been or there is a topology change. That gets communicated up to SW1 and across to SW3, and they run that spanning tree protocol algorithm all over again to decide what ports are going to be designated, what ports are going to be routes, what ports are going to be blocking, what ports are going to be forwarding, and it does so based on these timers here. We'll come on to that in just a few minutes. But what is that topology change note acknowledgement that you see here? Well, let's just say, for example, SW2, its interface has gone down here. I know it was blocking, but let's just say that this was a forwarding port, just for example. What it will do is it will send over to SW1. It's not going to send it down to SW3 because this interface is down, so that's just not going to happen. But it will send over to SW1 its topology change notification. And upon receiving this, SW1 is very quickly going to send that topology change notification onto the root bridge SW4. So first we send it over to SW1, and then SW1 sends it on to SW4, the root bridge. But as soon as that is done out on the SW1 side, it will then send back that topology change acknowledgement to SW2 to basically say, hey, I can see you sent me this BPDU with this type of TCN of a topology change notification. You notified me of something. I acknowledge that. And when the root bridge receives that topology change notification, guess what? It too will send back its own topology change acknowledgement to SW1 to say, yep, I got that as well. And then the root bridge, as I was just going through, will send out its new BPDU, which will be a configuration message with a topology change over to SW3, up to SW1, and across over to SW3, and that will be indicating that there is a topology change. So pretty fascinating stuff when you actually look at it. We've then got the root ID. We've already gone into this, and I keep erasing it. I really should stop that. But the root ID, so the root ID for all these BPDUs, once it's converged, will equal the MAC address of SW4. The root path cost is, say for SW2's perspective, what is my cost to get to that root bridge? And then the bridge ID is my own bridge identifier, my own systems, chassis, switches, MAC address. And because we've just been talking about SW2, let's just put SW2 there. And the port ID as well. So the port ID actually indicates two things. It is the priority of the port, which is a default of 128. Then it has a colon to actually identify the port ID as well. And all of that is communicated in this one header there. And then we come on to those message. And then we come on to these timers here. And these are very, very important in the STP world. And so here are these timers all the way from the message age to the max age, hello time, forward delay. Now, the one I'm going to concentrate initially on is the hello time, because really it's the most straightforward one. And there's actually two ways of getting the hello time out there, the hello message. I.e. you've got one from the root bridge, and then you've got the hello messages from the non-root bridges, such as SW1, SW2, and SW3. Now the hello message, it is obviously a protocol ID of STP, whatever that is, the version is STP, but under BPDU type this will be a configuration message, so config here, and in the flags nothing really is going to be set in here, it's just all going to be blank, so it's just going to be 0x00, just for example. But these are sent out every 2 seconds, and that is default. You can, of course, change that timer. So every 2 seconds, the root bridge will send out of its designated ports. Don't forget we've got designated port here and a designated port here. It will send out those hello BPDUs every 2 seconds out of their designated ports. And when the non-root bridges, the designated switches, receive this hello BPDU, they will forward that on to the other non-root bridges every hello timer, so every 2 seconds. So every 2 seconds they're expecting to receive a hello BPDU, and every 2 seconds they will forward that hello BPDU. And then we've got the forward delay, and the forward delay, just so you know from the start, is 15 seconds by default. And again, you can change that. Now let's recall those states, those port states. We've got blocking, and then you've got listening, and then there's learning, and then finally at the end you've got forwarding. Now what this forward delay timer basically means is how much time is there going to be spent transiting between these different states. So when we go from blocking to listening, we're going to do so immediately. And when we enable a port, so say you enable a port to be part of the span and tree port configuration, it immediately goes into the listening state. But when we get into the listening state, we are going to spend 15 seconds here. We are listening to BPDUs, but we are not forwarding those BPDUs. We're not learning any of their MAC addresses. We're quite literally listening to what's happening on the wire on that blocked port, for example. Because don't forget, maybe we've gone from blocking straight into listening. And then when 15 seconds has expired, we then move into the learning state, where guess what? There is another 15 seconds because of this forward delay. And now we are learning the MAC addresses. We're not receiving frames, but we are receiving BPDUs. We're not processing them, but we are learning the MAC addresses. But when we're going to do so for 15 seconds. And when that 15 seconds has passed, we then move straight into that forwarding state. And you can go from a forwarding state straight and immediately back to a blocking state. You don't have to pass through these forward delay timers. It just happens immediately. But we've got 15 seconds here and 15 seconds here. And so therefore, if you want to go from blocking to forwarding, just for example, that is going to take at least 30 seconds because of this forward delay timer. And what also happens here is that it's also used to age out the MAC addresses that are in the switching table. So if we look at it from switch W1's perspective, SW1, it will have a MAC address table. And in that table, it will store lots of MAC addresses of all hosts, tenants, servers, whoever, that have communicated for a certain period of time. And that certain period of time is by default around about 5 minutes. Now, when there is a topology change, what will happen is the switch will age out its MAC address timer, so it's no longer 5 minutes, but now only 15 seconds. And that's important because if there has not been any MAC addresses that have communicated in this 15 seconds, then they will have to be relearned, of course. But any MAC addresses that do communicate in that 15 seconds obviously will be maintained. And that allows that switch to have a trustworthy, a non-stale MAC address table. So it just adds a degree of stability and trustworthiness. But just note the forward delay timer, when there's a topology change, we'll come on to that in a few minutes. The MAC address table is timed out and the timer moves from 5 minutes to this forward delay timer here. And then you've got this concept of message age. For me, message age in my mind is like the IP TTL, or time to live. Basically, the further you get away from that source, the less trustworthy that configuration message in the spanning tree protocol will actually be. Now, in terms of the source, what we're actually referring to is the root bridge. So the root bridge will send out a hello BPDU, and within that it will have a message age timer, which by default is 20 seconds, just for example. But when SW1 sends this on to SW2, suddenly that message age is no longer 20 seconds. No, because we've had 1 hop or 1 second here. It's now going to be 19 seconds. And if there was a switch connected to SW2, just here, it would then be 18 seconds. And if there was another switch just connected here, it would be 17 seconds. Basically, what the switch is doing is it's taking the max age timer, I'll come on to that in a second, and minusing away that message age. So the message age at the root bridge would be 0 because it's the source. When it gets to switch W1, it will be 1. So it would be 20 minus 1 equals 19. When it gets to switch W2, because we've had 1, 2 hops here, I keep calling them hops, but it's really the same concept. Suddenly it's going to be 20 minus 2 equals 18. So it just gives a degree of trustworthiness in terms of that message age and that configuration that's contained within that current message. And then we've got the max age itself. As you can see here, indicates when that configuration message identified via the BPDU type, when that should be deleted. And again, this is 20 seconds. And if a switch ever gets down to 0 on this, basically that configuration is no longer valid, and it's going to start looking and generating those topology change notifications because it hasn't heard from that root bridge in a certain period of time, i.e. 20 seconds. I.e. what is the maximum age I can hang on to this configuration before I declare a topology change notification. And coming back to this message age, the further away you get to this root bridge, the lower trustworthiness this will be. So again, the message age will be 20 minus the certain hops away. So SW2 was 1, 2 hops away equals 2, and the message age would be 18 seconds. So let's now talk about when there is a topology change. And there is a question, what is determined, what dictates, what is meant in the spanning tree protocol world as a topology change? And that's why I've done this. So when a port transitions to a forwarding state, so it goes from blocking to listening to learning to forwarding, or, big word, or when a port in the learning and forwarding state transitions back to the blocking or disabled state, that is a topology change. So if we look at it from SW2's perspective, if this interface here suddenly, or this interface here suddenly changed state and this moved to a forwarding state, that would be a topology change, and that would then determine, and then that would then mean SW2 would take action. What action is that? I've already gone through this, but this is going to be a bit of a nicer slide. Well, first and foremost, SW2 has seen that there is a topology change, and as such, as I've already gone through, it is in its BPDU type going to define this as a topology change notification. It's not going to have any flags set, and you can actually see the header here. Note it's, well, the packet capture, note it's pretty blank, isn't it? It's just defining in that BPDU, so this would be part of a bridge protocol data unit, that this is for STP, and that the protocol version is just common spanning tree protocol, and that there has been a topology change notification, and note the hexadecimal values here. That's it. So this TCN is sent from SW2 over to SW1, and as I've already said, when SW1 received that topology change notification, the second step it does as quickly as possible is it just says, I need to get this TCN out as quickly as possible, and boom, it sends that out of its root port here to, in this case, the root bridge, or to the other non-root bridge that's connected on the uplink, depending on your topology, of course. And pretty much this will happen between step 1 and step 2. This will happen very, very quickly. And the third step, as you can see here, is that SW1, it will send back to SW2 its topology change acknowledgement. So here it's going to have a BPDU type of configuration. So it's going to be a configuration. But here in the flags field, we're going to give the acknowledgement. We're going to have the flags set to indicate that this is a topology change acknowledgement, i.e. SW1 is acknowledging back to SW2, I acknowledge that original TCN that you sent me in the first place. This all happens very, very quickly. Don't think that there's a delay to go from 1 to 2 and then to acknowledge again. It is extremely fast. And SW1 has sent that acknowledgement back to SW2, but the second step was for SW1 to send the topology change notification to the root bridge to SW4. And now the fourth step is, in this case, our root bridge SW4 here. It's going to send that topology change acknowledgement back to SW1 and say, yep, I can see your configuration BPDU type. I can see that you sent me a, it's going to say, yeah, I can see your topology change notification BPDU type, and I am going to set my flags to again give you a TCA, I'm acknowledging your notification. And just a little point here, as you could see, so just a key takeaway, the switch will send out its topology change notification every hello interval. So again, the default for the hello time is 2 seconds. So when a switch sees a topology change as defined here, it will send out that topology change notification every 2 seconds. And this is the packet capture of a topology change acknowledgement that will be flagged in the flags header. And note, for the protocol identifier, it's saying, yep, it's STP, it's using this hexadecimal value. The protocol version also identifies, is it STP, is it RSTP, etc. This is, the BPDU type is a configuration message, but note under the flags, it's set to 1 here, and this is given a topology change acknowledgement indicated by yes. And all of this other really cool information that really you see here as well. But note the max age set to 20, the message age set to 2. So this would be from a switch that's at least 2 seconds or 2 hops away from that root bridge. We could see the forward delay timer. We could see what is the originating VLAN. We could see the MAC address of that particular switch, and we can also see what is the MAC address of that root bridge as well. So pretty cool, interesting stuff. And then you've also got the path cost. What is my path cost to get to that root bridge? And so let's go through 2 examples of a topology change when you've got a layer 2 network running spanning tree protocol. Now, by now, I'm sure you are more than familiar of this network here and the actual setup, i.e. switch 4 here is the root bridge, and it's going to have its designated ports, and right here between switch 2 and switch 3 is a port that is actually blocking. But what happens in example 1 when the interface between switch W2 and switch 3 goes down? It's disabled, it's unplugged, it's just disconnected. What happens in that event of a topology change? Well, the first thing to really notice and to point out is that traffic is not really impacted by this topology change, because as I just said, the interface between switch W2 or SW2 and switch 3, it's already blocking. It's all, I wouldn't say disabled, because that just means it's not participating in STP, but it's already blocking. It's not allowed any traffic to really go over and to be received on this interface. Yes, it's still listening to BPDUs, but it's not really doing anything with them. So here, when that link here actually goes down, the traffic isn't really impacted by that. But still, it is a topology change nonetheless, because the port here has seen that, I have been forwarding and I have been a designated port, but now this link is down. And as such, between SW3 and SW4, so from this switch to the root bridge switch, there is going to be the generation of the BPDU to indicate within the BPDU type that this is a topology change notification. SW3 is going to tell SW4, the root bridge in this case, that there has been a change, and I am making you aware, I'm notifying you of that topology change. And because this is a root bridge, it doesn't need to then send that TCN onwards, doesn't need to do that, because this is the root bridge. And as such, what the root bridge SW4 will do is it will send that topology change acknowledgement back. So under the BPDU type, this will now be a configuration BPDU, and in the flags it will have the topology change acknowledgement flag set. And what happens next? The next step, because the root bridge has been made aware of that topology change notification in really the first step here, and it's already sent out the topology change acknowledgement here, is it still needs to make all other switches, including SW3, which sent that topology change notification, aware of a topology change. To be honest, the root bridge doesn't really care that this topology change notification has come in on this port, and I don't need to send the topology change BPDU out of that port. It doesn't care about that. It's just going to say, even if I've received this TCN on this port, I'm still going to send that topology change BPDU out of that same port. And that's basically what you're seeing here. So the root bridge SW4 is going to send a topology change. So here we're going to have a configuration BPDU, and in the flags you're going to have that topology change flag actually set, and it's going to make SW1 aware, and even the generator of that TCN message SW3 aware that there has been a topology change. And as it says here, SW4 will send out the BPDUs with that TC flag set to both SW3 and SW1, and of course any other switches that are connected to that root bridge. And so at this point, SW1 has received that topology change flag, that topology change BPDU from the root bridge, but because it's got a designated port in the forwarding state to another switch, which just happens to be switch 2 in this diagram, it's going to forward that topology change notification on to SW2, even though the SW2 has that interface between SW2 and SW3. It is blocking. It's not really seeing that the interface has gone down. It's not even generated that topology change notification, because SW3 actually really saw that and really cares about it. But we still need to make SW2 aware that there has been a topology change, and maybe it needs to do a reconvergence, needs to rerun that STP algorithm. And as I just said, note, and I really just said this, but the SW2, it didn't send that TCN message because the port was already in the blocking state. And when you move from a blocking to a disabled state, so this would no longer be blocking, this would be disabled, that does not, from SW2's perspective, mean that you have to send that TCN message. No, because that does not count as a topology change. And as such, the time to do a reconvergence when you've got a link going down, in this case between a blocking link on one end of the interface and of course a forwarding designated port on the other end, the total time to reconverge is 0 seconds. So in that case, STP is pretty fast, but that's when there is a disconnection between a switch or two switches and one of those interfaces just happens to be blocking. And that is actually based on this setup here. So if you've got a different setup, different architecture, it could be different, but theoretically, but because there's no transition to go from a blocking state to a disabled state, that's really 0 seconds. And that was the end of example 1. Now we're moving on to example 2. So what happens when, if this was blocking, I've removed it for just the reason of this illustration, but what happens when the interface between SW1 and SW2, and both of this was a designated port and this over here was a root port, and both of these were forwarding, what happens when that interface goes down? That's what we're going to explore here in terms of that topology change. Well, unlike the previous example, when this link goes down here, traffic will be impacted until, that's the big word there, until the STP, the spanning tree protocol, that link path cost back to the root bridge, etc., until all of that fully reconverges. So SW1 has seen that this link has gone down. What does it do? It does exactly the same thing that we've learned by now through this series, through this episode. That switch, SW1, will send out a topology change notification upstream out of its root port. And it just so happens that the next switch along is the root bridge itself, i.e. SW4. And when SW4 sees that topology change notification, it will change the BPDU type to be a config message, and as we know now, the flags will have that TCA, that topology change acknowledgement set, and then it will send that back to SW1, i.e. hey, I'm the root bridge SW1 and I've seen your topology change notification and I am now acknowledging that. And just like before, that root bridge SW4 will send out a BPDU, that is everything you see here as we know, and it's going to have that topology flag set. Hopefully you know by now that topology change flag is going to be set in here, and the BPDU type, hopefully we know that that will be a config message, i.e. switches, I am the root bridge, I'm sending you a configuration message, and the flags is indicating that there has been a topology change, and it's sending out that BPDU to SW1 and to SW3 and any other non-designated root bridges, i.e. non-root bridges switches, tongue twister, that are connected to it. I just send that out of all of its designated ports. And interestingly as well, the root bridge, it will continue to do this for 35 seconds. Now that doesn't mean that the convergence with such a failure is going to take 35 seconds. No, what it means is that the root bridge will continue to send out this BPDU with that topology change flag set for 35 seconds. And this is due to those timers, the max age and the forward delay timer. As you might recall, hopefully recall, max age is basically how long a switch will keep that configuration in its database, in its memory, and trust it's there. And then we've got the forward delay timer, which is the time to transition between those different transitive steps, i.e. listening and learning. So 35 seconds, 20 seconds plus 15. So it's just going to send out that BPDU for 35 seconds. Now this next part is different to example one, and it's really quite interesting to learn about the STP process. Now what will happen is two things in this next step, or these next two steps for obvious reasons. So first, when SW3 has received that topology change notification from that root bridge, it is also receiving a topology change notification from SW2, because SW2 has seen that link go down. This used to be its root port, but now all of a sudden it's disabled. But it knows that it's got this interface here, and this interface is no longer going to be blocking. No, it's actually going to assign this as a root port. And as such, it's just going to send out of its root port a topology change notification, i.e. this interface here has gone down. But at the same time, SW3 is getting from that root bridge this topology change. And as such, that topology change notification that's coming from SW2, at a look at it there, it is what's called inferior. And it's inferior because SW3 knows that SW4 is the root bridge. It already knows its bridge identifier. It already knows its priority. It already knows its MAC address. And it can see that SW2's priority is higher. You can see that SW2's MAC address is higher, and thus it is not as preferred. That's what is meant by inferior. So really, the messages coming from the root bridge are still superior compared to SW2. And so SW3 knows, as I just said, that SW2 is inferior. But again, when any switch boots up, loses connectivity out of its root port, it's going to assume it's the root bridge and just send out that the root bridge identifier is equal to its own bridge identifier. It's just going to assume it's the root bridge. But SW3 is receiving these TCNs, and really for the first 20 seconds for that max age timer, it's going to ignore them. It's just going to ignore them until that max age timer times out. And then it's going to acknowledge that TCM. And when that max age timer has timed out, it then sends that topology change notification, that BPDU that it got from the root bridge. Is going to forward that on to SW2, and at that point SW2 learns that hang on, SW4 has a better priority, or it has a lower priority and maybe a lower MAC address. We know how a root bridge is elected, and so it now basically says, okay, SW4, I am not the root bridge. And thus it can now determine the next stage, because it knows it is not a root bridge. It just knows from that this port here and this port here are not going to be designated ports. They're going to be either a root port or maybe a blocking port. And so SW2 at this point has elected this port to be its root port, as we know that is going to be based on the lowest cost to get back to that root bridge. And it is going to have this as a root port, and that is going to be in the forwarding state, and the interface adjacent here is going to be a designated port and also in the forwarding state. Now the interface, the link between SW1 and SW2, which end will be blocking, which one will be a designated port, what does that depend on? Well, again, it depends on the bridge identifier. First the priority value, then, as we know, the MAC address, and if that is a tie, then it depends on the link priority, and of course then the link ID. So it doesn't matter, one of those ends is going to be blocking, and thus it is going to break any loop in that network. But based on this topology, it will take 30 seconds at least to reconverge. Why is it 30 seconds? It is because this interface here has to transition from a blocking state to a forwarding state. So it has to go from blocking to listening to learning, and then finally to forwarding. And these two are transitive states, and each one takes, as we know, 15 seconds each, which gives us, guess what, that 30-second reconvergence time. So there we go, two quick examples of what can happen in a topology change, and there are more. 0 seconds in example 1 was best case scenario. 30 seconds is okay. You can get topology changes which take 50 seconds at least, or maybe longer. It depends on the scale of the network, of course. But just know that STP at the end of the day does take a long time to reconverge. You can see that here. No one wants to have a network down even for 30 seconds. That's not going to be good for any business. And thus, there are more preferred STP variants such as RSTP, which I'll be doing in a later video. And so there we go, everybody. That is the end of this video. That is the end of this part on spanning tree protocol. We've gone through a lot of information. We've gone through what is STP, why was it actually created, what were the challenges that we saw on networks before STP came around, what is a root bridge, how is a root bridge actually elected, and that's the first stage in STP converging. And the second stage in STP convergence is deciding on what ports are going to be root port, what ports are going to be a designated port, and what ports are going to be in that blocking state to prevent those layer 2 loops. And then we went into a little bit more detail into that BPDU, that Bridge Protocol Data Unit message, and all the different headers from the flags to the root ID, to the link cost, to the timers, and even went into the timers and why they're so important to STP. And finally, just finishing with 2 examples at the end. So as always, I hope you found that useful. Hope you found that informative. If you like my content, please give me a thumbs up. It's the best way to support my channel. Any questions or comments, let me know down in the comments box. I love hearing from you all. Other than that, thanks for watching and goodbye.